I would like to introduce our keynote speaker, Professor Olivier de Weck. Ollie is a professor of aeronautics and astronautics, as well as engineering systems at MIT. He's one of the world's eminent scholars in systems engineering, and particularly how complex man-made systems such as aircraft, spacecraft, automobiles, critical infrastructure, and of course, consumer electronics are designed, and how they evolve over time. Professor de Weck started his distinguished career in the Swiss Air Force. He was also a program manager for the F-18 aircraft at McDonnell Douglas, and he has been on the MIT faculty since 2001. Ollie also currently serves as the editor-in-chief of the Journal of Systems Engineering. Ollie will start off our conference today by speaking about the philosophy and the theory of modularity. So please join me in welcoming Ollie de Weck to the stage.
Thanks, Paul. Good morning. How is everybody? It's great to see you all, and I'm very, very excited. You're about to make history with Project Ara. It is really a paradigm shift, and I want to talk to you about some of the theory and some of the enabling scholarship behind modularity. So let's get started. And I want to start with this. Rube Goldberg. Who's familiar with Rube Goldberg? Quick show of hands. Okay, not too many of you. So Rube Goldberg was a very famous cartoonist in the US, and he built or basically designed these outrageous machines that are super complex and kind of silly, actually. This is one of my favorite. This is the automatic back scratcher. So let me just talk you through how this works. Starting on the left side, we have a lamp that is burning and whose flame catches a curtain B on fire. The fire department sees this and sends water through the window. C, a dwarf D thinks it's raining and reaches for the umbrella E, pulling down the umbrella, pulling on the string F, therefore tilting the platform G in the middle, causing the lead ball H to fall down, pulling down the string I, and rotating the hammer G such that it breaks the glass plate K. This noise wakes a puppy L, and its mother pup M starts to rock it back to sleep, rocking the cradle N back and forth. This, in turn, moves the handle O gently up and down, scratching the back. So great. Rube never built his own machines, by the way, so we don't really know if it works, but we think this machine is probably very unreliable. The question is, is it modular? Is this a modular machine or not? In order to answer that, we need to think about the functions and how those functions map or are implemented in modules or parts or elements of form. So let's think about this 2x2 matrix. And the way you read this is from the top down. On the left side, we have systems where each function is clearly assigned to or executed by a particular element of form or part or module, such as the example here is a VLSI chip, very large-scale integration chip, where each part of the chip has a very specific function. This is clearly a modular architecture. On the lower left, we have, as an example here, a sextant. A sextant is, of course, used to measure angles in the sky for navigation. It is one function, but in order for that function to happen, we need many different parts that are connected in intricate ways. You take one of those parts away, and the whole function doesn't work. So that's integral. One function, many parts. The upper right, we have a single part. This shows here a cast or molded part. It has a lot of complex details. Physically, it's one part, but it provides many different functions. That's also an integral architecture in a somewhat different way through function sharing. And then the lower right, we have an example here, a car door assembly, and it is somewhere in between. It has a coupled architecture, many functions, many parts. So where does a Rube Goldberg machine fall in this space? In the lower left, right? It has one function, scratching the back, but it requires a complex combination of parts. You remove only one of those parts, and the whole thing collapses. It doesn't work, okay? That is not what Project Ara is about. Project Ara is really about the upper left, a modular architecture where each module provides a very well-defined and very well-contained function. Most of the traditional devices that we see on the market today are much more in the lower right-hand corner. They're integral, and the mapping of different parts of those devices to functions is very complex and not clearly modular, which has a lot of implications that I'd like to talk about next. So we're about the upper left corner here, where each function is clearly assigned to a part or module. So key questions that we ask and scholars have asked about modularity for many years. How do we define and quantify modularity? What are the styles of modularity that exist? What are the benefits and downsides? And maybe the most important is, when is a modular architecture superior to a functionally equivalent integral architecture, the ones we saw in the lower right-hand corner? And finally, for today, how does modularity enable or relate to the Google Ara platform? So I'd like to talk about these three things in some more detail. First of all, summarize for you some of the key ideas and key concepts in modularity, specifically the idea of styles of modularity. What are the styles? Number two, we'll talk about quantifying the degree of modularity in a system and understanding the tension that we have between the business objectives and the technical constraints, particularly around the packaging constraints and the power constraints that you'll hear a lot about today in detail. And then finally, I'd like to share with you an initial modularity analysis that we've been working on with the Ara team, showing you how different combinations of modules can be put together using compositional rules and how customers might react to these different combinations of modules. All right, so let's take a step back and think about where we are today in 2015 in terms of the big picture industrial paradigms. On this graph, I'm showing you on the y-axis, on the vertical axis, product variety. How many different variants can we produce in terms of the total number of products we manufacture? The dashed line 1.0 essentially means every product you make is slightly different, okay? If you're below the line, it means your products look more and more similar. If you're above the line, that's actually an interesting question that we'll talk about in a minute. The x-axis is simply your production volume. The further you are on the right, the more units you manufacture per year or per unit time. So let's think about where we started. Craft manufacturing in the Middle Ages. We had skilled artisans manufacture by hand with a lot of knowledge, a lot of experience, systems like clocks and shoes and weapons and household goods and so forth. And they were limited, of course, by their manual capacity. So they manufactured at a low production rate, and every unit was slightly different, was slightly unique. That's craft manufacturing. We then started to move to the right and down. So in the US, for example, we talk about AMS, the American System of Manufacturing, essentially that started in the armories, trying to make rifles, for example, whose parts could be exchanged. And then further accelerating that in the early 20th century into the mass production paradigm. Mass production means you're making millions and millions of identical things. So we're in the lower right-hand corner. What happened then in the second half of the 20th century is that we started turning the corner. The demographics of population, the ability to manufacture in smaller batches allowed us to do mass customization. And that's really where we've been in the second half of the 20th century. Where are we today? Today, we are, for the first time, really moving above the line and still to the right. We're still growing. The world population is growing. The number of people who have access to technology is growing. But what's exciting now is that a single device can be so many different products at once. So the variety within a single product is actually exceeding above the line. And Project Ara is really one of the pioneers in configurable or reconfigurable products. And so that's very exciting to really contribute and be a part of this revolution of shifting industrial paradigms to reconfigurable systems. So how does it work? One of the key things about the Ara platform is the idea of a two-sided market. Two-sided markets have been around for a while. For example, newspapers that place ads and mediate between the people who place ads in newspapers and the readers of the newspaper. That's a classic two-sided market. Another example is, for example, gaming platforms, where you have developers who develop games and consumers who use these platforms to play games. Both sides of the market are in relation to each other. And the market is mediated, in the case of the Ara platform, by the endoskeleton and the standard behind this particular platform. So on the left side, we have the users, potential users, who join the platform because they see value in it, because it offers something that's distinct and different from competing products. On the right side, we have the developer community, and we're hoping that many of you will become actual developers and will join this platform. The key to enabling this are the modules. The variety of modules and the classes of modules that are necessary to populate this platform. The more modules are available of different kind, the more attractive the platform becomes to the users, and the more likely they are to join. And the more users are in this ecosystem, the more likely you as developers will join the two-sided market. And the modularity is really the key to enabling this, and not just the initial startup of this two-sided market, but also its evolution over time. So let's talk a little bit about the definitions of what we mean by modularity and how to quantify modularity. What is really a module? It's an easy question, but the answer is not so simple. You can think of a module as any collection of parts that belong together as a set and form a distinct subsystem. The key is that the modules are really in the eyes of the beholder, the designers, the makers, and the users of the system. And the intent of a module can be for various reasons. For example, we can form modules for implementation, to make implementation and assembly of the system easier. And that's typically what we call assemblies. So it's easier to integrate. It gives some flexibility to manufacturing to create variety. Or, and this is an interesting thought, we can empower the users, the consumers, to take advantage of the modularity to configure their own devices. So think about a Google Ara device that is in a particular configuration for every day. You go on a business trip and you swap the modules so that your phone is better adapted to what you're about to do, or when you're on vacation. So the idea that the modularity empowers the user to optimize the operations. And then finally, in the longer term, modularity can be an enabler for better servicing, better evolution, and better upgrading of the product, rather than simply disposing and throwing away the product when it doesn't meet your needs any longer. So the key to this, and I guess this is a point where all of you will have to think very carefully, is product decomposition, architectural decomposition. At the highest level, there's a set of requirements that the system as a whole or the module has to satisfy. And when you choose your high-level concept, you essentially choose the functions and how those functions will be implemented in hardware and software. This has to then be broken down at the lower level, -1, -2, and so forth, until you reach the lowest level. The modularity is really the key to mapping those functions at the high level to elements of form, and this is recursive at every level of the product decomposition. Let me show you an example. Paul introduced me as an aerospace engineer, and it's true, that's where I had my start. So here's a well-known system in aerospace. This is the Pratt & Whitney 4098 engine. This is a direct drive, two-spool turbofan engine that is used, for example, on the Boeing 777 aircraft. And it's a very complex machine. It has 9 subsystems, 54 components, 569 interfaces, and those interfaces are physical, information, energy, and mass exchanges. If we look at the connectivity structure or design structure matrix of how these parts connect and interact, we get the picture on the right, this matrix with the red and purple entries. This is essentially the decomposition of this particular engine. And if we reorganize that slightly, we can see that there are modular subsystems which are labeled on the plot. The fan, the low-pressure compressor, the high-pressure compressor, the burner and diffuser, those are all modules that fulfill a very particular function in the primary and secondary airflow of the engine. And then we have the distributed systems or utility systems that hold the engine together. That's the structure, it's the lubrication, it's the FADEC or engine controls. So what particular style of modularity are we looking at when we look at an aircraft engine? So this leads me to the discussion of styles of modularity. There are 3 fundamentally different styles of modularity that have developed over time. And let me start with the one at the bottom. This is what we know as sectional or as slot modularity. So in slot modularity, we have a modular system, but the modules fit together in only one very specific way. You can only assemble, think of a complex jigsaw puzzle. If you make one mistake, the system doesn't work. It only fits together in one particular way, and there's not a specific standard. So our aircraft engine that we just looked at is, in fact, slot modular. Let's move to the top. Sectional modularity. What does this mean? This means we have a very specific interface standard, and every module can connect with any other module in arbitrary ways. The classic example here is USN, a very well-known furniture manufacturer. They, in fact, build sectional modular furniture that gives you a lot of different possibilities. Every module can connect to every other module. And then the third type of modularity, and that's the one that is relevant to the Ara platform, is so-called bus modularity. The modules cannot connect with each other directly. They can connect to each other indirectly through the common bus element. So bus modularity, the bus itself is the specialized element where all the modules hook into and communicate with each other through the bus. So a bus modular system is what we're looking at with the Ara platform. Okay, so let's move on to how we quantify modularity and the tensions that we need to resolve between technical and business objectives when we think about creating a modular system. So don't be scared here about these equations. I'll try to make them sort of simple. The first one is actually very simple. M1, this is the sort of simplest modularity metric that's been proposed by Carl Ulrich about 20 years ago. And the idea is that a perfectly modular system has a modularity index of 1, meaning that you take the number of functions that your product provides and you divide it by the number of components or number of modules, depending on the degree of abstraction. If that number is 1 or close to 1, you have a modular system. If the number is greater than 1, it means that we're in the upper right corner of that 2x2 chart. Many functions provided by very few parts. Or if the number is smaller than 1, it's the opposite. We need a lot of different parts working together to achieve a particular function. The second metric is the scary one, but it's in fact relatively simple. You take the design structure matrix of the system, and module by module, you need to manually define the module boundaries, which parts are in each module. You look at the density of connections in each module, and you subtract from that, the second term, the average density of interfaces in the rest of the product. And then you do this for all the modules and look at the average density within the modules relative to the average density of the whole system. Again, if that number is 1 or close to 1, it means the density is you have very high density in the modules and no density, no connections outside the modules. And then the third one is one that we came up with about 10 years ago. We started tearing down different products, building these design structure matrices, and then doing what's called a singular value decomposition, also known as principal components analysis, and plotting the principal components. Essentially, this is the spectral signature, if you want, of the architecture of the product. And we compared pairs of products, like a desk phone and a cell phone, or a desktop PC and a laptop. And we noticed that the spectral signature of more modular or more integral products was very different, and repeatedly so across different classes of products. And therefore, this particular modularity index looks at the decay rate of the singular values of the product architecture. So the faster the decay rate, typically the less modular the product will be. And so you can then compare pairs of products that are essentially functionally equivalent, a static version of the product versus a mobile version of the product. And even though the numbers here in this table are very different for these 3 different modularity metrics, the message is the same, that traditionally mobile products were generally less modular as predicted by all the 3 metrics. And this is, the key here is that over the last decade, miniaturization has now progressed to the point where this paradigm can be broken. In other words, we are now at the point where, due to miniaturization, the mobile products can be as modular as products that don't have the weight or packaging constraints that we see typically in mobile products. So this is a kind of exciting, another paradigm shift that the Ara platform will enable. So let me summarize the principles of modularity that have emerged over time. So first of all, generally from a business or customer perspective, a high degree of modularity is very desirable because you can create more variety, you can reuse the modules across different architectures. It's a good thing. For the engineers and the software and hardware engineers, this is a bit more challenging. A higher degree of modularity typically is challenging to achieve, and there's two primary reasons for that. One is the power efficiency and the power levels, and we'll hear quite a bit about the details of this today, can limit your modularity choices or make it challenging to be modular and power efficient at the same time. One of the technical reasons for this is impedance matching at the interfaces. You need to match the impedances at the interfaces as perfectly as possible, or you'll have inefficiencies and losses. And then the other is, of course, the packaging and lightweighting constraints. Typically, modularity carries some amount of volume and mass overhead on the order of 10 to 30%. And in the first spiral of the Ara platform, this was looked at, and the penalty, if you want, for the modularity is somewhere in that range, 10 to 30%. But again, we think that because of miniaturization, it's now the human factors, the eyes, the hands, the way that people interact with the device that are the limiting factor and no longer the technology itself. The third point here is that in terms of software, modularity is also a good thing. It makes the code more transparent. It makes the code more easy to maintain. And usually there's no or little penalty for this. There are some exceptions which are real-time embedded systems, really where every millisecond counts. There you have to also look at, in a more modular software architecture, what the impact might be for real-time embedded systems performance. The summary here is that advances in technology and miniaturization have shifted the old constraints and enable today mobile modular devices that we couldn't have built maybe just 5 years ago. Let me come to the third piece, and maybe this is the most exciting. This is essentially how does modularity and the possibilities that modularity opens up impact the Ara platform and the ecosystem that we talked about, this two-sided market. If we think about this two-sided market, and we've been working with Paul and his team at Google on developing an agent-based model of this two-sided market. It has 4 fundamental building blocks. First of all, the platform itself, and the platform is characterized by its cost, its performance, the number and type of available slots. So I'm showing you here the medium platform, the medium-sized platform. And of course, that platform then enables, but also provides some constraints to the actual modules that will live on that platform. We'll talk about the classes of modules, the levels of innovation, and of course, there are questions around price and recurring costs of these modules. On the left side, we have the users. Those are the customers and adopters. Different users have different preferences and are more or less sensitive to the uniqueness of their device. And then on the right side, we have you, the developer community. Each of you has different experiences and capabilities. A big question that we know you have is around what are the development costs, what are going to be the actual costs of the device, and what are the gains that are to be had by joining this particular platform. I'd like to focus now on the modules themselves and the module choices. So in order to understand, since we don't really have much experience with this type of modular device, we started out by looking at existing phones and existing sort of the ecosystem of existing phones, even though we think that Ara will produce devices that we haven't even conceived yet. But there's quite a bit of data from the existing users in terms of what's important to them and what's less important. And so this data that we obtained from the GSM Arena, many of you are familiar with this website, allowed us to essentially map the performance variables on the left, performance variables K, to factors that drive the satisfaction of individuals with their phones. So each individual who responded to the survey would indicate the degree of satisfaction they had with their particular device. And since we know the performance characteristics of the device, we can then map those particular attributes to the different classes. So on the right side here, I'm showing you 12 different classes of modules. The first 6 are screen, the audio modules. So this is the particular the modules that enable voice commands and oral communications, the battery, the processor, the storage, and then the encasement and the appearance of the device. And then we see a lot of potential classes of sensors. Sensors are going to be very important, and a lot of these sensors are things that have never been built in a mobile device before. So we can now map user preferences against module classes in terms of the degree of preference or satisfaction. Let me show you briefly here some of the data that we found based on the existing user community of traditional phones. The upper chart shows you the normalized preferences for particular performance attributes. And as you would expect, things like camera resolution, battery talk time, standby time, screen resolution, also the capabilities of the processor are very important. And self-identified here are 5 different types of users. People that are primarily consider themselves as texters, talkers, social communicators, surfers, or app junkies. Their preferences are not dramatically different, but you can see that there are some slight differences. And those preferences are then mapped to the 12 classes of modules, modules J, in terms of the particular preference structure of these users. What can we do with this? Well, we can now think of these 12 module classes in terms of optimized modules in green. Those are modules that are essentially based on current technology that's currently available and is optimized or repackaged to fit within the platform Ara standard. In the middle, we have modules that are extensions of current, that are novel, but they're fundamentally extensions of current technologies. And on the right, we have what we call radical modules. These are really unprecedented in terms of what they can provide and what technologies they implement. So let's keep those colors in mind as we move forward. The question then is, let's say we had a library of these modules, a mix of modules. What are the rules, the compositional rules by which these modules can be connected to each other? And what you see here on this chart is a so-called DS2M. It's a design structure matrix, but it's a design structure matrix not for a particular architecture, but for the universe of all possible combinations. So for example, if you want to use a particular sensor, that module requires the presence of a processor, and the processor requires, of course, the presence of energy storage of a battery. And so there are interdependencies between these modules. We call those interdependencies compositional rules. Going through this allows us to then generate topologies or combinations or bundles of modules that satisfy the feasibility and the compositional rules, which we can then evaluate. So let me show you, and I have to point out, these are preliminary results. This is not final, but it's very promising. So based on this approach, we were able to generate 3,072 feasible module bundles, combinations of modules, and each of them is then evaluated against the preference set for the 5 classes of users I talked about a couple minutes ago. And so this allows you to plot the first cost, so this means the initial acquisition cost for the platform and the modules that sit on that platform, versus the degree of satisfaction that users might have. And each of the points, each of the dots on this chart represent a very particular combination of modules, a very particular architecture. And so what you can see is now that with one platform, with the Ara platform, on the lower left, you can essentially replicate the functionality of existing feature phones. In the middle, we're moving into the domain of the smartphones. And then in the upper right, these are advanced devices. These are essentially devices that are unprecedented, where there is no competition or no comparison for them in the market. So and we're particularly interested, of course, on the ones that are close to the lower right-hand corner, because that is the efficient frontier. Maximize satisfaction for minimum cost. So let's take a look at scanning all the way from the lower left, a basic phone or gray phone, as we call it on the Ara project, all the way up to really advanced devices. And so as we scan that Pareto frontier, We have on the top something like a basic phone, and you can see that it contains essentially repackaged or optimized modules based on existing technologies. And as we move to the upper right-hand corner, as we move lower on this table, we see more yellow modules and more red modules appear, meaning there's a lot more new technology, there's a lot more unprecedented modules that start appearing in the module bundles. So a quick example here. On the left side, this is what a basic phone might look like. This is architecture 1452. Its normalized price is 1, and the degree of satisfaction is 0.47. And it's a fairly basic device. It has audio and screen. It has storage. It has an environmental and a movement sensor. It has a processor. And in fact, 2 of the slots, the lowest 2 slots, are empty, are not utilized. So you could add modules in the future. On the right hand, we have an advanced device in the upper right corner. And you can see a lot more yellow and red. So we have advanced modules for optical sensors, cameras, advanced batteries. We have perhaps an advanced processor. And then the appearance of the device is also customized. And there might be an upcharge for this kind of combination of modules. In this case, maybe 64%. But it essentially gives you an idea for the flexibility to customize and shape the device along that universe of potential combinations. So let me wrap up by saying that we're very excited to be a part of this. And one of the unique things about the Ara platform from a customer perspective, user perspective, is of course that your initial phone, your initial device, for example, if you started with one of those simple phones in the lower left-hand corner, you're not stuck in that corner forever. You can evolve your phone by adding, deleting, and swapping modules over time. So the question is, what are the optimal pathways through that space for evolving your device in the future while maximizing satisfaction and optimizing the net present value of the device or the platform for the developers and the platform owner? So let me summarize. Questions that we asked early on: how do we define and quantify modularity? Modular systems have a clear functional assignments to elements of form, and they have a higher degree of coupling within compared to across the whole product. 3 styles of modularity: sectional modular, bus modular, which is what the Ara platform is, and slot modular. The benefits of modularity are many: greater product variety, module reuse and swapping, and enabling the evolution of your device. There are some downsides, inefficiencies due to power and packaging constraints, but we're pretty confident that those can be overcome. When is a modular architecture superior to a functionally equivalent integral architecture? It's essentially the case when the extra benefit or satisfaction you get from customizability and evolvability of the product outweighs these downsides. And finally, how does modularity relate or enable the Google Ara platform? Since the Ara platform is bus modular, you can generate thousands of feasible product configurations optimized for different individual users while adapting the device over time. Thank you very much.